All right, 5.9 is another relatively light section in your book, which I guess is kind of nice. The idea for 5.9 is we're kind of going backwards. Right? We spent all this time figuring out how to determine the area underneath the curve. In other words, determining definite integrals. And we started out with basic forms and then learned these really advanced methods of integration so we could do it in really clever situations, use substitutions, integration by parts, etc. And then in the last section, we are like, oh, and you got all these tables that you can default to if you need to. We're really good with integrations. In fact, we're done. We're done figuring out different functions that we can find antiderivatives of. But as I talked about in the last video, it's a little bit problematic because there's lots of functions out there. Let's see, one that's commonly cited is the square root of 1 plus x cubed. If somebody asked you to find the antiderivative of this, they'd be messing with you because this function's antiderivative is not an elementary function. In other words, you can't figure it out. And it's not you can't figure it out because you're not good enough at Calc 2. It's you can't figure it out because an answer does not exist, or at least there's no answer that we can write using the mathematical notation that we have. So what do you do in this situation? What if somebody really wanted to know how much area is there underneath this curve from 1 to 3? We can't use the evaluation theorem because we can't come up with an antiderivative, but I guess what we could do is estimate the area under the curve. Okay, realistically, it's 20/20, and if you're trying to estimate the area under the curve, you'd go to a computer and you'd have the computer estimate the area underneath the curve. However, understanding the methods that the computers use to estimate the area under the curve, I guess has a little bit of meaning. So what we're going to do in this section is we're going to learn, or we're going to do more with estimating the area underneath the curve. And if you remember well, we already did that, right? We learned how to estimate the area underneath the curve because we used these formulas to derive the limit of sums formula that we used our first time when we were trying to calculate the area underneath the curve before we learned the evaluation theorem. We could use left endpoints or right endpoints, and all we had to do was add up a whole bunch of rectangles, n rectangles, and the area of each rectangle is the width of the rectangle times the height of the rectangle, and the width of the rectangle, delta x, is given by this formula. And figure out the height of the rectangle, you just think about what function you're talking about and plug in the appropriate x value, which is given by this formula. I know it's been a while, but there was a point in the class when you were pretty good with these two formulas. And I could give you a function like y equals x squared, and I could ask you to estimate the area underneath the curve from 1 to 9 by calculating, I don't know, L4 maybe. L4 would be the sum from I equals 0 to 3, because playing the role of n in this formula is a 4. Of delta x f of xi, but delta x would just be 2 in this case because playing the role of b would be the 9 and playing the role of a would be 1, and 9 minus 1 is 8, and 8 divided by 4 is just 2. And then to figure out my I values, I take a, which is 1 in this case, and I add I times delta x, so I get 1 plus I times 2, or 2i. And this, in sigma notation, can be expanded to be 2 times f of 1, because when I equals 0, 2 times 0 is 0, and 1 plus 0 is just 1. So 2f of 1 would be my first term when my index is 0, plus 2 times f of 3, because when my I changes to 1, I have 1 plus 2 times 1, and 2 times f of 5, and 2 times f of 7. And I stop when I get to f of 7 because my index stops when it reaches 3. And when I equals 3, I got 2 times 3 is 6, plus 1 more is 7. So to estimate the area underneath the curve using left endpoints, I'd figure out the heights at 1, 3, 5, and 7, and make the rectangles according to those heights. So you can kind of picture my last rectangle right here. And I'd calculate the area of each of those rectangles individually, and I'd add them up, and I'd get my answer. In this case, since f of x is relatively easy, it's just x squared. Exponent should be in the superscript, not the subscript. I don't know what happened there. At any rate, since y is just x squared, f of 1 is just 1 squared. So I get 2 times 1 squared, plus 2 times 3 squared, plus 2 times 5 squared, plus 2 times 7 squared. And then I can add these all up, maybe make my life easy by factoring out a 2, 1 squared, 3 squared, 5 squared, 7 squared. I wonder if I've done this exact same example. It's certainly possible. Let's see, I get 50 and another 34. That's 84, I believe. And 2 times 84 is 168. What I'm saying is you could estimate the area underneath this curve using left endpoints, and you would estimate the area to be 168. However, we know that the exact area underneath the curve is just the integral from 1 to 9 of f of x, which is x squared in this case, dx. And since we're so good with the evaluation theorem, it's super easy to take the antiderivative of this guy. It's 1/3 x cubed, evaluated from 1 to 9. I get 1/3 times 9 cubed minus 1/3 times 1 cubed. And let's see, for the sake of calculating this, maybe I pull the 1/3 out in front, and then I figure out that 9 cubed, 9 times 9 is 81. 81 times 9 is 729. And then 1 cubed is just 1, which is what, 728 thirds? Or Google tells me that that's equal to 242 2/3. Note that the exact answer is quite a bit bigger than this approximation. Oh, that's not surprising because I use left endpoints. Each of these different rectangles that I draw is going to miss a whole lot of area. At any rate, L4 is a poor estimation, but it's one way you can estimate the area underneath this curve. That all ring a bell? Well, guess what? There's other ways you can do this. You can also estimate the area not just using left endpoints or right endpoints, but using midpoints. And all midpoints does, here's the formula for it, is it's kind of the same idea, but for this last rectangle here, which left endpoints estimates the height using 7, and right endpoints estimates the height using 9, it goes from 7 to 9. What midpoints would do is it would estimate the height using 8. So it'd be like, well, the height at 8 right here is, what is that, 64. So I could draw my last rectangle using midpoints to look more like this. That's all. If you want to use midpoints, the way you figure out the x values to put into your function is by finding kind of the average of what you would use with left endpoints and right endpoints. So this last rectangle, my left endpoints tells me it would be 7, my right endpoints tells me it would be 9. If I take 7 plus 9 and divide it by 2, I get 8. This is just a mathematical way of expressing that each of these different rectangles, the one that goes from 1 to 3, from 3 to 5, and from 5 to 7, we're going to estimate the height by using the midpoint of that rectangle. So 2, 4, 6, and 8 in this example. It typically gives a little bit better of an estimate than either LN or RN, and you can get the answer this way. I'm not even going to bother demonstrating that for you. I think you could do that if you wanted to. The point of this video is just to say that there's lots of different ways you can do it. In addition to left endpoints and right endpoints, you can use midpoints, or you can also use trapezoids or Simpson's rule. And these are the two that I'm going to demonstrate for you, and these are the two that I'm going to kind of consider the bulk of this section. So the idea with trapezoids is you're not going to use rectangles at all. If I wanted to estimate the area under the curve by calculating T4, then what I'm going to do is instead of using 4 rectangles, I'm going to use 4 trapezoids. And the way the picture goes is to draw each of the different trapezoids. Maybe I'll just draw one of them for you. My first trapezoid will go from 1 to 3. My next one will go from 3 to 5. My next will go from 5 to 7. My last will go from 7 to 9. In case you don't remember what a trapezoid looks like, I'll try my best to superimpose one on top of this graph. There we go, I tried my best. The idea with the trapezoid is you have one set of parallel lines, so it kind of sort of looks like a rectangle, except the top of the rectangle is slanted. It's a trapezoid, not a rectangle. If only you knew some geometric formula that would figure out the area of a trapezoid. It turns out that the formula for a trapezoid, what you do is you multiply the height of the trapezoid, and height is a weird term to use because this one's kind of on its side, but height is really the distance between the two parallel sides. And you multiply that by the average of these two lengths, the average of the lengths of the two parallel sides. You probably learned that in a geometry class way back in the day. You don't have to worry about that. That's all encoded in this formula. So what I'm saying is the height, and that's in quotation marks because now delta x represents the height of the trapezoid, the distance between the two parallel sides, gets multiplied by the average of those two lengths. F of xi minus 1 represents this length right here, and f of xi represents this length right here. So what I'm saying is it's very similar to the midpoint formula. In the midpoint formula, we found the average of the two x values. The average of 7 and 9 gave us 8, and 8 squared gave us 64, and 64 is what we multiplied by delta x. For the trapezoid formula, you find the average of the two y values because you add up the two y values and divide them by 2. The y value over here, we calculate by taking the x value of 7, putting it into this formula. So 7 squared is 49. So this y value is 49. The y value over here is 81 because 9 squared is 81. And 49 plus 81 divided by 2, that ends up giving you 65. So to figure out the area of this trapezoid that I gave you right here, what you would do is you take delta x, which is 2, and you would multiply it by 65. If you didn't follow any of that, it doesn't really matter because it's just a formula and you plug in numbers. It turns out that if you expand out this sigma notation, it turns into this. You can take the 2 and factor it out in front with the delta x. So the delta x and the 2 end up here. And then x0 appears once when I equals 1. It shows up right here because this is I minus 1. But x1 appears twice. It shows up when I equals 1 over here because the I is 1, but it also shows up when I equals 2 because when I equals 2, 2 minus 1 is 1, so it shows up here. So what ends up happening is all of the terms except for the first one and the last one appear twice in this sum. So you can just memorize that it's f of x0 plus twice f of x1 plus twice f of x2 plus twice on and on until you get to the last one. So in this specific example, what would happen is I would use f of x0. X0 is 1. That would only show up once. X1 is 3. X2 is 5. And x3 is 7. And each of those would show up twice in this summation. And then the last one, x4, which corresponds with the 0.9, would only show up once. Let me show you that. So copying this version of the trapezoid formula for T4, so my n will be 4. So my sum is going to go all the way from x0 up to x4. And the coefficient on f of x0 will be 1. And the coefficient on f of x4 will be 1. But all the rest of the coefficients will have a 2. And then I'll have delta x over 2 out in front. Yields this expression. Note the 2's on all the terms except for the first one and the last one. And then delta x and xi are the exact same that they were when we calculated them above. For this example, maybe I should write it out. Delta x is b minus a over n, so 9 minus 1 over 4, because remember n is 4 here, so I get 8/4 or 2. And then xi is a, which is 1 in this case, plus I delta x, so plus 2i. So what I'm saying is x0 is just 1 plus 0 2's. x1 is just 1 plus 1 2. x2 is 1 plus 2 2's, and so on. Since delta x is 2, I have 2 over 2 out in front, which I'll just get rid of in the next step. And then replacing x0, 1, 2, 3, and 4 with 1, 3, 5, 7, and 9, I get this expression. And evaluating this expression is easy enough because f of x is just x squared. So 2 over 2 is just 1. F of 1 is 1 squared, or 1. F of 3 is 3 squared, which is 9, times 2 is 18. 5 squared is 25, times 2 is 50. 7 squared is 49, times 2 is 98. And 9 squared is 81. And if I could add up this sum, what I would have is the estimate for the area underneath the curve using 4 trapezoids. And it's kind of annoying, but I think the numbers work out. Let's see, 19 and 81 is 100. How convenient. And then 50 and 98 is 148. So 100 plus 148 gives me 248. But whatever, it's just a number. It's not even the right answer. But note, it's quite a lot closer to the real answer, which is 242 and 2/3. Than it was when we used left endpoints and we only got 168. Oh, that makes sense. If I drew trapezoids in between 1 and 3 and 3 and 5 and 5 and 7, it would do a fairly good job of tracing out this curve right here. My picture is not great, but I think your book does a little better job. Here. Right here's the curve. You can kind of see it in blue, and they're talking about putting all these different trapezoids in between and figuring out that area. And you can see that you get a much better approximation than you do if you use right endpoints or even midpoints for that matter. I think this picture right here does a much better job of anything that I've shown you in this video. It's worth pointing out that there's one more estimate that I'm just going to show you the formula, and then I won't even do it for you. It's called Simpson's rule. And all Simpson's rule does is instead of using rectangles or using trapezoids, it uses parabolas. So I think in this example, pink is the actual function that we're trying to figure out the area underneath, and we can estimate that, and we do a pretty damn good job of it using these different parabolas. A parabola kind of connecting P0, P1, and P2 is sort of shown in blue here, and then another parabola connecting P1, P2, and P3 is next shown in blue here, and then 2, 3, and 4, and 3, 4, and 5, and so on. And they calculate these parabolas, and they derive the whole thing in here. And I don't know, I guess it's an interesting read if that's your thing, but really all you need is the takeaway, which is this formula right here. And I wrote this formula in the notes. The key thing to know about this formula is it's kind of like the trapezoid formula, where it's easier to not deal with it in sigma notation and jump straight to the expanded form. Except instead of delta x over 2, you need delta x over 3. And that comes from that derivation that's in the book. Frankly, I wouldn't worry about it at all if I were you. The other thing that's different is instead of the coefficients on the ends being 1 and all the rest being 2, the coefficients on the ends are 1s, and all the rest alternate between 4s and 2s. So it starts with the 1 and then goes 4, 2, 4, 2, 4, 2, 4, 2, all the way until you get to a 4, and then you get back to a 1. And you can be like, how are you guaranteed that you'll end up with the 4 when you alternate them in the second to last term? Well, it's because n must be even for Simpson's rule to work. And if n is even, the way these will alternate is you will always have 4 as your second term and 4 as your next to last term. So I can't ask you to do S7, it doesn't make sense, but I could ask you to do S6 or S8. We could even do S4. It would look a lot like this formula here, except it would be delta x over 3 instead of 2. And it would be 1 and then 4, 2, 4, and then 1 here. So if you change this to a 3 and this to a 4 and this to a 4, you'd get the estimate using Simpson's rule. And what you'll see is it's an even better estimation in this case than the trapezoid rule. And I'm not even going to bother. I'm going to leave that to you because I think it's kind of just trivial at this point. You're just changing a couple of numbers. The whole idea for approximating integrals is, hey, there's other ways you can approximate them. And there's 3, I guess, new ways to us in addition to left endpoints and right endpoints. Midpoints, but that's not even interesting enough for me to even give you examples of. The examples I want to show you are trapezoids and Simpson's rule. And if you know kind of intuitively that trapezoids are, instead of using rectangles, using trapezoids, and Simpson's rule is, instead of using rectangles or trapezoids, kind of using parabolas, loosely speaking, then you could just take these formulas as given. You certainly do not need to memorize them. I'd always provide them for you. And you can estimate areas underneath curves using them. And the logic for doing so is there are functions out there that we can't figure out the antiderivative of, so we might need to use these. But what you'll see is those functions are ugly enough that I'm not going to ask you to use these to estimate them anyways. What I typically do is ask you to estimate the area under a curve, even though you could calculate the area under that curve, because that curve is so simple we can find its antiderivative in the first place.